Right. So you probably noticed, if you were paying attention last week, that we only got to one of the learning targets that I put up at the start of the lesson, being able to state the events of the formation of the universe in the order that they happened. Well, I've got good news. Today, we are going to get to that second part. By the end of this lesson, you are going to know what evidence we have to support the Big Bang Theory and which parts of the theory each piece of evidence supports. So, today we're getting into what makes this a scientific theory, the evidence that it fits. And remember, this isn't like a hypothesis where we came up with an idea of what happened first and then went out looking for evidence to support or disprove it. The way a theory works is that we had this body of evidence and came up with an explanation that fit it best and then modified it as we got new evidence. So here we are, still on this big question that we're striving to answer. How exactly did the universe get to be the way it is today? And we start with what we start with for so many different scientific concepts. We start with an ongoing argument. We started out with two major schools of thought. Either the universe as it is now has always existed exactly the way it is now, or the universe had some kind of beginning and has changed over time. This was the earliest version of this argument, infinite past versus finite past, and we've been having it since about the 300s BC. On the infinite side of the argument were ancient philosophers like Aristotle. And this argument didn't sit well with a lot of people, particularly with religious scholars, and especially Islamic scholars like Al-Kindi, Sadia Gaon, and Al-Ghazali. And these scholars had a variety of alternate theories, but they all boiled down to the universe hasn't always been like this because we have all of these traditions that say that the universe has a starting point. Interestingly, the first theories that started to look like our modern ideas of how the universe worked were put forward by poets Erasmus Darwin, grandfather of the more famous Charles Darwin, and Edgar Allan Poe. This, of course, was back in the time where men could be dabblers in as many fields as they wanted because they had women and slaves to take care of all the more practical concerns of keeping them alive. But none of this was what would really hold up as a scientific theory today. It wasn't evidence-based. Even Sir Isaac Newton stuck his hand in on this argument with some mathematical modeling, but again, not evidence-based, just math. And that was the state of things until we started to gather some pretty key pieces of evidence. So let's look at that evidence. We've got 6 key pieces to look at, and we're going to go through them in the order that you see here, which means that we're going to start with Hubble's law or universal expansion. All right, so let's start at the beginning. We know that the Big Bang, as we've conceptualized it, was more like an inflation. Actually, hang on. Let's get rid of this slide for a second. Right, put the slide away. Let's have a visual. So here I've got a balloon. It is purple because purple is the color that I like to use for space. So on this balloon, I'm going to grab a Sharpie here, and I'm going to draw 2 points. It's 1, 2. There we go. So now I've got a balloon that looks like it's got 2 eyes on it. And I can measure how far apart these points are. Grab a ruler and flatten my balloon out a little bit. And they are exactly 3 centimeters apart. Couldn't have done that better if I tried. Now, what happens if I start to blow up this balloon? Let's find out. There we go. Pinch that off for a second. And I'll bet that you can tell just by looking at it that my 2 points have gotten farther apart from each other. But for the sake of accuracy, let's measure. And it looks like they are now about 5 centimeters apart. And if I keep going, it's hard to even see the 2 points on screen at the same time anymore. You can't, because they've gotten farther apart. Specifically, they are now 11 centimeters apart. And I could keep going until the balloon popped. Anytime it expands, those 2 marks that I made are going to get further apart. So if the universe is expanding, what that means is that every point in the universe, just like those 2 points on my balloon, is going to be moving farther apart. This would happen with any 2 spots that I had drawn anywhere on that balloon, and it works the same way for the universe. If something goes from something very small to something very massive, all of the points inside of that something are going to move farther away from each other. And that is exactly what Edwin Hubble observed in 1929 when he was working at the Mount Wilson Observatory in California. You don't need to worry about recording the dates that I'm going to give you in this, by the way. I just want to give you some context for how this is playing out over time. So, Hubble was completely unaware that 2 years before this, a Catholic Monsignor named Georges Lemaitre had proposed a theory based on the math of Newton and Einstein that said basically, okay, if Newton and Einstein have it right, and we've got some evidence at this point that supports some of their ideas, so if all of their ideas are right, the universe must be expanding. He wasn't the only one to come up with this idea, but he's the closest one to this time point. But we still have no evidence. It's purely mathematical. And even Einstein, who is still alive and working at this point, was reluctant to endorse Lemaitre's ideas because there was no concrete proof. So Hubble's work was incredibly important, even though he didn't know it at the time because he had no idea about Lemaitre's research. But Hubble observed 2 key pieces of information based on the work of 2 scientists that came before him that let him work out that the universe was expanding. And that information that he observed had to do with how far stars were apart from one another and what color they were. So let's backtrack a little bit here. A little more than 10 years before Hubble's discovery, to Henrietta Leavitt. And Leavitt was a volunteer in the observatory at Harvard who was hired full-time and eventually came to run their photometry department, which was concerned with taking data about the brightness of stars. And Leavitt discovered something interesting. See, Leavitt observed that there were certain kinds of stars that change in brightness over time in very predictable ways. They cycle from bright to dim, back to bright. These kinds of stars are something that Leavitt observed and took data on and did math with, and she discovered that there was a direct relationship between how long the star was at its brightest and how large the star was. And once you knew how large a star was, it was very easy to calculate how far away from us it was. So Leavitt published these findings in 1912, and they were groundbreaking because before this, we could really only accurately calculate how far away things were from us up to about 100 light years away using the parallax method that some of you read about if you did the stars reading on Actively Learn. But Leavitt's calculations let us accurately calculate the distance of objects that were as much as 10 million light years away. A major, major expansion in our ability to understand things that are far away from us. And it turns out that 1912 was a pretty big year for the study of space because in that same year, Vesto Slipher, who hands down wins for coolest name in this narrative, and who is also famous for supervising the folks that discovered Pluto a couple decades after this, was looking at galaxies and found something weird. They were a little bit redder than they ought to be. So, remember when we talked about spectroscopy? We know that based on what elements a star is made of, it emits certain colors of light. And furthermore, we know that we see a certain banding pattern in that spectrum that is a characteristic of the elements that it's made of. Well, Slipher was looking at spectra of distant galaxies and comparing those spectra to spectra that were given off when the same elements that those galaxies were thought to be made of were burned on Earth. And he noticed that, for example, he would see the right pattern of dark bands for sodium, but it wouldn't be at quite the right wavelength. So if you take a look at that image that I put on this slide, you can see how that works. So that top band would be sodium on Earth. In the next band down, you can see the same pattern. The lines are all the same distance apart from one another, but they're shifted just slightly to the right. And that's what Slipher was seeing when he looked at his spectra. He had a ready explanation for this. And yes, that pun was completely intentional. You're welcome. Thanks to the work of another scientist named Christian Doppler, for whom the Doppler effect is named. See, it works like this. Right, so I have here a pipe cleaner. It is purple because purple is the color that I associate with space, once again. And it's nice and flat. And I'm going to form this pipe cleaner into the shape of a wave. Here we go. Well, that's a little bigger than I wanted. We're going to make a smaller wave. Just by bending my pipe cleaner back and forth to make kind of a snake shape. There we go. We've got a wave here, forming up pretty nicely. Here it is. There, pretty even wave. And let my fingers be two objects. Say over here is a star, and over here is me. And this wave would represent that light coming from the star to me. And right now, the star and I are not moving. What happens then if all of a sudden I get in a rocket and start traveling towards that star? Well, as I start to get closer, you see the wave scrunches together. So as the two things get closer, the wavelength gets shorter. And the opposite is true too. If I get in my rocket and start moving away from the star, my wave stretches out. So now we're farther apart than we were at the beginning, and the wavelength of my wave has gotten much longer. We call this effect the Doppler effect. And you can actually observe this for yourself with sound waves anytime an object is moving past you and making noise. Ambulances, ice cream trucks, neighbors who like playing really loud music when they drive, all of these are great candidates for observing the Doppler effect in action. As an object that's making noise moves closer to you, the sound waves get pushed together. The resulting pitch that reaches your ears is higher than it would be if you were sitting inside of the noise making vehicle because the waves have been pushed closer together as that thing approaches you. So the wavelength is smaller and the frequency is higher. And as the object then moves away from you, once it's past you, the opposite happens. The wave gets stretched out, lowering the wavelength and the frequency, and therefore lowering the pitch. With light, we call these effects blue shift and red shift, respectively, because as the wavelength of light gets smaller, it gets closer to the blue violet end of the visible spectrum. And as the wavelength gets longer, it gets closer to the red end. So, what Slipher was seeing was that 12 galaxies that he was observing had a red shift. And based on that, he could calculate how quickly they were moving away from us. Now, Hubble gets all the credit because he was the one to take these two concepts, the period luminosity scale and the red shifting concept, and put them together. And what he observed and what he figured out from that was incredible. He looked at galaxies and he used Levitt's scale to calculate how far away they were from us. And then he used Slipher's methodology to calculate how fast they were moving away from us based on how redshifted they were, and came up with what we now call Hubble's law. The farther away two objects in space are from each other, the faster they are moving away from each other. In other words, Hubble was able to demonstrate empirically, with data, that the universe is expanding. We saw that with my balloon, too. The bigger it got and the farther away those 2 points were, the faster the distance between them changed. When the balloon, I just inflated it a little bit, it went from 3 centimeters to 5 centimeters. That's a change of 2 centimeters. But then when I inflated it more, it went from 5 to 11, a difference of 6 centimeters. The farther away they got, the faster they moved apart. So consider your timeline from last week. Which of our points along that timeline have to do with expansion? Those points, we use Hubble's law as evidence. Hubble's law is far and away the most complex of our pieces of evidence. So we're going to move through the other 5 a lot more quickly, I promise. So far we have evidence that the universe was once smaller than it is now and has expanded and is still expanding. Let's move on. And the piece of evidence that we touch on next, some of you, if you looked at that image gallery from NASA to try and determine which were false color images, may have been exposed to already because you may have seen this image. And this is very obviously a false color image if you know what it's an image of, because this is a picture of empty space. And if you take a telescope out and you take a look through it, or if you go outside and you stand up and look at the sky after dark, you know that space is black. Space is empty. Except it's not empty. We just can't see what's there because what's there isn't visible light. But space is full of energy, specifically electromagnetic waves, and more specifically, microwaves. So here's how this one shook out. In the 1940s, a couple of physicists at Johns Hopkins were trying to figure out the temperature of space. They came up with a prediction that space had a temperature of about 5 Kelvin, but their work didn't really go anywhere because astronomers really weren't interested in taking the universe's temperature at that point. So their work went pretty unremarked, apart from a couple of scientists agreeing with their math, until the 60s, when Arno Penzias and Robert Woodrow Wilson were doing some experiments with satellite communications and had a problem. See, their satellites worked with microwaves, and their instruments were constantly picking up an antenna temperature that was 4.2 Kelvin higher than it should have been. This discovery won them a Nobel Prize because what they found was a snapshot of the universe in the moment that it became transparent to electromagnetic radiation as it cooled. What their instruments were picking up was the leftover radiation from the start of the universe. We can actually observe in this radiation the way that photons have cooled and redshifted since the Big Bang. So, considering your timeline, you're going to want to record this as evidence wherever you talked about electromagnetic radiation and the cooling down of the universe. Now, the cosmic background radiation is critical for another reason, because it was pretty much the nail in the coffin for a competing theory, steady state theory. See, go back to that argument that we talked about at the start of this lesson. Not everybody was too keen on the idea that the universe had a starting point that it grew from. And up until this point, there was a theory that competed with the Bang, which we call steady state theory. And what steady state theory was at this point, at one point, it had been basically that same Aristotle argument that the universe was always the way it was and is always going to be the way it is. And the discovery that the universe was expanding forced that theory to change a little bit. So at this point, what steady state theory said was, okay, yes, we understand that the universe is expanding, but it is constant throughout. It has always been this way. And no matter where you are in the universe is made up of the same stuff. This idea is grounded in our understanding of how forces work. If, say, gravity acts the same way everywhere in the universe, we should expect the universe to reflect that and be pretty much uniform throughout. It's a very tempting idea, but there were some major problems with it. For starters, now that we add in the idea that the universe is expanding, this theory requires that somewhere new matter has to be being created to expand outwards to keep everything constant throughout. And right away, I'm sure that some of you see a problem with that. See, we've got that law of conservation of matter thing that says that you can't just create matter out of nothing in a closed system. So, this implies that the universe is an open system, that there's some external source of matter that's getting fed in to keep the universe constant. Now, this idea was already on the ropes due to some other stuff like quasars, which we'll talk about in a minute, but cosmic background radiation pretty well killed it because we could see this energy and we could see that it was changing over time, that the universe was cooling. And that just didn't work with steady state theory because that energy had to come from somewhere. And the way that it was behaving let us know that it was changing over time. So, this was pretty big defining evidence that steady state, the competing theory for the history of the universe, just didn't work at all. Right. So far we have evidence that the universe is expanding, and we have evidence of that first release of electromagnetic radiation. Now let's get to the weird stuff. And boy, if you're looking for weird, quasars are right up your alley. So, a quasar, which is short for a quasi stellar object or QSO, is defined as, let me put on my fancy terminology scientist hat, an extremely luminous active galactic nucleus in which a supermassive black hole with mass ranging from millions to billions of times the mass of the sun is surrounded by a gaseous accretion disk. So basically, From here, quasars look like incredibly bright stars, but what they actually are glowing black holes, which is weird because black holes are pretty well known for being, dark, black, kind of right there in the name. But wait, because it gets weirder, because quasars are only found in the 10 to 15 billion light years away from Earth range, and nothing exists past them. Or rather, we can't see anything past them. Quasars are great evidence for the timeline of the growth of the universe and how it developed. Because, see, we talked last week about how galaxies formed and how it started with nebulae, where dust sticks to other bits of dust due to gravity, and things just keep attaching and attaching until overwhelming gravity causes them to collapse, forming the beginnings of stars. Well, that's what we see happening in a quasar. And that light, that is old light. It took 10 billion years or more to get to us. So a quasar is kind of like a time machine. It's allowing us to look back into the history of the universe to see what it was up to 10 billion years ago. So if you take a look at your timeline, what would have been happening in the early universe about that point? Those quasars, they're another big death knell for steady state theory, like I mentioned earlier, because remember, steady state says that the composition of the universe is the same throughout. The stuff that the universe is made of in our stellar neighborhood is the same stuff that it's made of everywhere else. So, if that theory worked, we should see quasars everywhere spread throughout the universe, because the composition of the universe should be consistent throughout. But we don't see that. Instead, what we see is that things closer to us have moved on past that quasar state to look more like the galaxy that we know and love, the Milky Way, the one that we live in. So, quasars let us look back in time to see what things might have been like in our neighborhood 10 billion years ago. So, for those of you keeping score, we have evidence that the universe is expanding. We have evidence of the first release of electromagnetic radiation. And we know roughly what the universe was up to at the 10 to 15 billion years ago mark. Moving right along, the last three pieces of evidence are a lot more straightforward, and they're going to require a lot less explanation. And the reason they take less explanation is because they're things that we've already talked about, like, say, radioactive decay. This one's pretty straightforward. We know that radioactive things have half lives. That is, how long it takes for half of what was there to decay to some more stable state. So we can look at things like moon rocks and know how old they are. And we can look at Earth rocks and know how old they are. So this is going to start to fill in some timeline information about how our solar system developed. For example, we know that the moon is older than the Earth. So we've got estimates from radioactive decay and radiometric dating that tell us the relative ages of things in our solar system. And here's another one that you know a lot about already. We have telescopes, we have satellites. We can use these things to look at stars. And we have, and we've watched them grow and develop. So we have a pretty good understanding of how stars form and how long it takes them to go through the various parts of their life cycles. And then finally, and very closely related to how we use quasars to understand the universe, we know that light has a speed limit. Light travels at a constant speed pretty close to 300,000 kilometers per second, which is incredibly fast, but it's still a speed limit. Light takes time to get from one place to another. And when we're talking about things that are the size of our entire universe, it takes a lot of time. So, how old is the universe? Well, we can tell that because we can measure how far the farthest light has traveled to get to us. So, here we are back at our list of evidence. And there you have it. This is how we know how the universe got to be the way it is today. Now, here's what you're going to do with this information. Remember that timeline that you hopefully made last week? Well, you're going to add to it this week. For each of the events that we talked about this week, you should be able to work out which evidence matches with it. So, if your event is that the universe is expanding, what's our evidence of that? If your event is this is when the universe started, what's our evidence of that age? You're probably going to use some of these pieces of evidence in more than one place. And you might find that you've got more than one piece of evidence for your time points. That's okay. Make sure, as you fill this into your timeline, that you explain what this evidence means. So don't just write Hubble's law in the evidence box and move on. Include what we know because of Hubble. And how is that related to this time point? So, if because of Hubble we know that the universe is expanding because it's redder than it ought to be, you make sure that you put that on your timeline. I know that this was a long one, and I know that there was a lot of information in there. I'm glad that you stuck with it until the end. And do not be afraid because we're going to keep working with this information for the next little bit just to solidify everything and make sure that you know how all of the pieces fit together. So go do good work. Be good, be safe, be kind. Don't do anything I wouldn't do. Remember to wash your hands.